Today we're talking extrema. So these are global mins and maxes, or also called absolute min and maxes, or relative min and maxes, which we also call local min and maxes. We're going to start by defining what extrema are. So let f be defined on an interval I containing c. So f of c is a minimum of f on the interval I when our y value, f of c, is less than or equal to all the other y values on our function. It's a maximum when our f of c is greater than or equal to all the other y values on our function. All right? The minimum and maximum of a function on an interval are extreme values or extrema of the function. And the minimum and maximum of a function are called the absolute or global mins and maxes. Okay? So the extreme value theorem. If f is continuous, so here's the conditions. If f is continuous on the closed interval a comma b, then f has both a minimum and a maximum value on the interval. So it has to be defined on the endpoints. Okay. F has to be continuous on the interval. Okay. Wholes and values that go to infinity do not count as maximums. So an absolute maximum would be this value here. This is an absolute min, or a global. We also call it a global min or a global max. Okay. Here on the middle example, since we have a hole on the end on the right hand side, this is no max. It's a hole, and it would be the highest value. Okay. The lowest value here is a max. So just kidding. Low is a min. Okay. It's an absolute min. Here, because the values go to infinity, we have no max or min. Okay. Unless we restrict the domain. So if we said that the domain was between A and B, then we would have endpoints and we would have a min and a max. But since the graph is going through to infinity and positive infinity, we have no maxes or mins. All right. So another type of extrema is relative mins and relative maxes, and they occur inside of an interval. Remember from pre-calc that relative maxes are the top of a hill, and the relative min is the bottom of a valley. Relative extrema, so relative mins and maxes, can equal the absolute mins and maxes as well. So let's identify these mins and maxes, relative mins and maxes. Go ahead and do that, and I will do it on my paper as well. All right, so I've identified my relative maximums as the top of the hill and my relative mins as the bottom of the valleys of the graph. We're going to actually find the values of our relative mins and maxes without our calculators. So we were able to do that in pre-calculus with our calculators. So now we're going to use some calculus to figure these things out. All right, so we need to figure out what critical numbers are really quick, and because we're going to use them to figure out our relative mins and maxes. So we're going to let f be defined at c. So it's just a value. If f prime of c, so f prime of a number, is equal to 0, so has a 0 slope on our function, or if the function is not differentiable at c, so a sharp turn, a jump, something undefined, then then c is a critical number. So critical numbers come from zeros of your derivative and undefined things that make your derivative undefined. Okay, so relative extrema, the reason why this is important is that relative extrema occur at critical numbers. And so if f has a relative minimum and maximum at x equals c, then it is a critical number of f. So in other words, if we are a relative min or a relative max on our graph, then that is going to be a critical number from our derivative. But not all critical numbers are relative mins or maxes. If we have the graph f of x, we are looking for slopes that are 0. So when f prime of x is equal to 0, or when f prime of x is undefined. Those are our critical numbers. Okay. So we're going to find the absolute min and the absolute max in this video, and then we're going to find the values of relative mins and relative maxes in 2 videos from now. Okay. So this is how we do it. We know that an absolute min or an absolute max of a function will be found at either critical numbers or the endpoint. So either critical numbers or the endpoints of an interval. So we just have to kind of check those values. So what we're going to do is first, we're going to find the absolute value, the absolute min and the absolute max of this function on the interval -1, 2. Okay. So what we need to do first is find the derivative. We want to take f prime of x and find the critical numbers. All right, so I have f prime of x is equal to, so power rule, 12x to the third minus 12x squared. So that's my derivative. Critical numbers are values that make our derivative undefined or zeros. So I'm going to set f prime of x equal to 0. So 12x cubed minus 12x squared. I'll factor out 12x squared, giving me x minus 1 is equal to 0. Zero product property says I can have x equals 0 or x is equal to 1. These are my critical numbers. There's no undefined values, so I don't have to worry about those. The next step is to test the critical numbers. So we're going to test critical numbers in f of x to see which value is the largest and the smallest, okay? Because absolute maxes can happen at any relative max or the endpoint. So let's see. I have f of, so I have to test critical numbers and endpoints. Okay, so I have to test f of -1, f of 0, f of 1, and f of 2. Okay, so what we're doing is we're taking our original function here and we're plugging it in for each one of these. So I have 3 times -1 to the 4th minus 4 times -1 to the 3rd, and that equals 7. And then I have 3 times 0 to the 4th minus 4 times 0 to the 3rd is equal to 0. Okay, when I continue this, I get -1 and 16. And then it's a matter of who wins, okay? Whose value is an absolute max or min, okay? So our max is at the point, our max value is f of 2. So I have a max value at y is equal to 16, and it's at the point. Sometimes they ask for it at the point at 2 comma 16, and the min is at the value y is equal to, and I just look at these. So which value is the smallest? It looks like f of 1, okay, with a y value of -1, or at the point, 1, whoa, 1 comma -1. Okay, and I'm going to pause and continue the video a little later. All right here, I have pictured the graph of f of x, and this is the original f of x. You can look and see that at what we had was the endpoint was at 2, x equals 2, and x equals -1. And we're looking for the absolute min and the absolute max. So I have critical numbers at 0, 1, and the endpoints at -1 and 2. So when I tested our values into our original function, I can see that we have a absolute min at, whoa, I put a 2 there, that's a 1, at x equals 1, and an absolute max in this interval at x equals 2. Okay, so that's the visual of that. So we go ahead and try it on your own and then check. So f prime is equal to power rule 2 minus 3 times 2/3 would be 2 minus x to the -1/2, reduction of power. Then we're going to find our critical numbers, which remember are undefined values. So undefined values and, oops, the cube root of x. So I can see that we're going to have an undefined value when x is equal to 0 because of the denominator. And then to find the zeros, I'm going to set 0 equal to our derivative. Okay. And I get, let's move the 2 over. It's -2x to the -1/3. And then divide. So 1 is equal to x to the -1/3, and it seems easiest for me to just multiply by raise a power to a power, so I'm going to raise to a -3. Yeah, a -3. So 1/3 times 3 gives me 1, so this is x to the first power equals 1 to the -3rd power, and that would equal 1 over 1 cubed, so just in case, which is just 1. All right, so we have two critical numbers here, which is x is equal to 0 and x is equal to 1. So now we need to test. So we're going to test in f of x. Our candidates are our endpoints. So we're going to test x equals -1, x equals 0, x equals 1, and x equals 3. So f of -1, f of 0, f of 1, and f of 3. All right, I'm going to pause and put the work on the paper. All right, while it's getting there. Okay, I did this by hand, but you can do this in your calculator. But you probably should know how to do it by hand. Just remember that base raised to the 2/3 is the base squared, and then you're taking the cube root of that. So I get for f of -1, I get -5. It's -2 minus 3, which is -5. And I get 0, -1, and I get 6 for f of 3. I get 6 minus 3 root 3 of 3 squared, or cube root of 9. So this is about equal to -0.240, 3 decimal places. Okay. So who wins? We have an absolute max and an absolute min. at the point -1, 5, and our max is at the point 0, 0. So I just look, 0 is my highest, and our lowest was -5. Okay. All right, next up, you guys do this one. I'll take a minute. So I'm going to take f prime is equal to, and I don't like my function written like this, so I'm going to write cosine x squared times the sine of x. I can see that this is chain rule. Okay, so I do 2 times the inside, which is cosine x, and then the power reduces to a 1, times the derivative of cosine is negative sine of x, plus the derivative of sine would be cosine x. All right. And I will just make this prettier. So -2 cosine x sine x plus cosine x. And now we're going to find our critical numbers, which are nothing makes cosine or sine undefined. So I don't have to worry about undefined values, is none. Okay. But zeros, yeah, we got to do those. Okay, so 0 is equal to -2 cosine x sine x plus cosine x, and I'm going to use some zero product property here, factoring out cosine x, giving me -2 sine x plus 1. And now, since I have factors, I can zero product property. So I get the sine of x, just kidding, I get cosine of x is equal to 0, and -2 sine x plus 1 is equal to 0. Cosine inverse, or I know that cosine ratio is 0 when x is equal to pi over 2 and 3 pi over 2. And just remember, we're in the interval 0 to 2 pi, so I don't have to keep finding more coterminal angles. And then for the sine part, sine of x is equal to 1/2. So sine is equal to 1/2 when the y value is 1/2, so pi over 6. And then on the second quadrant in 5 pi over 6. Okay. All right, so these 4 values I need to test. What other values do I need to test? My endpoints. Okay, so I'm going to test these, and then my endpoints are x is equal to 0 and 2 pi. All right, so we have f of 0, f of pi over 2, f of 3 pi over 2, just put this over here, f of pi over 6, f of 5 pi over 6, and f of 2 pi. Yeah, that's a lot. Okay, so from the original, our original function is cosine squared x. I'm just going to write. So I have cosine squared of 0 plus the sine of 0. Okay, and then cosine squared of pi over 2 plus sine pi over 2. Okay, let's start with those two. So cosine 0 is 1, and cosine and sine 0 is 0, so this is going to equal 1. Cosine pi over 2 is 0. So, and sine pi over 2 is 1. Okay. Then I have cosine squared 3 pi over 2 plus sine pi over 2. You can draw your little unit circle if that helps, or 3 pi over 2. So on the coordinate here, -1 comma, 0 comma -1. So cosine 3 pi over 2 is 0, and sine 3 pi over 2 is -1. Okay. So I get -1. We have cosine squared of pi over 6 plus sine pi over 6. I know cosine squared of pi over 6 is root 3 over 2 squared, and sine is 1/2. So I get 3 over 4 plus 1/2. 3 over 4 plus 1/2. Oops. Equals 5/4. Whew, it's getting tight over there. Okay, the last two, let's just give us a little more room. Okay, I have cosine squared of 5 pi over 6 plus sine of 5 pi over 6. 5 pi over 6 is the same as pi over 6, but with different signs. So cosine squared of 5 pi over 6 is negative root 3 over 2, but squared, plus 1/2. And so this is also going to equal 5 over 4. Oh, cosine 2 pi is the same as cosine of 0, and sine of 2 pi is the same as sine of 0. So I know this one is going to equal 1. Okay, so who wins? Who wins? Our absolute max is pi over 6 at 5/4, and also 5 pi over 6. So we just write it as pi over 6 comma 5/4, and 5 pi over 6 comma pi 5 over 4. And then our absolute min is our 3 pi over 2. So it would be 3 pi over 2 comma negative 1. All right, that's it.